For video 1 of solving radical equations, we're going to start by looking at the principle of powers. And what this statement says is if x is equal to y, then we can say that x squared is equal to y squared. But we can only go in this direction. So for example, we cannot say if x squared is equal to y squared, then x is equal to y. And here's how we can kind of disprove this statement that I just added. So we could note that 3 squared is equal to negative 3 squared. Both of them would be equal to 9. However, if we removed those squares, we cannot say that 3 is equal to negative 3 because they are not one and the same. So what we want to note here is that we only want to think of that line of logic, this if-then statement, in this particular direction. Let's go ahead and actually work with a radical equation. And as I have noted on the right side of the screen, we know that we are dealing with a radical equation where we have a variable that is actually a part of the radicand, or in this case, is actually representing the radicand. So if we're trying to solve for this equation, our first goal would be to get rid of anything outside of the radical sign. So I'm seeing that I have a plus 7 that's happening outside, so I can go ahead and I can clear that out relatively quickly. So this is going to leave me with the square root of x is equal to negative 5. Now we might kind of notice maybe at this step a couple of red flags might be coming up, because again I'm telling you that the square root of something is equal to a negative number. And if you recall what we had learned about the principle of square roots, this is problematic. But I'm going to keep going just to kind of continue to illustrate my point here. So the next thing that we need to do is we can go ahead and apply the principle of powers at this point. So if I'm working with a square root, then I can undo the square root by squaring both sides. Again, because I'm working with an equation, what I do to one side of the equation, I must do to the other. So this is going to leave me with x is equal to a positive 25. When dealing with radical equations, it's a great idea. In fact, I really am going to stress that you should do this to check your work before you kind of settle on your final answer. So let's go ahead and do a check. So I'm claiming that x is equal to 25, so I'm going to substitute 25 in for x, and I'm just going to make sure that I get a true statement here. So the square root of 25 is 5. 5 plus 7 is 12, but I'm getting a statement that says that 12 is the same thing as 2, so this is incorrect. What I want to be aware of here is that while this came out as a solution, what we want to note is that this is an extraneous solution. Kind of emphasis on this extra here. So in other words, an extraneous solution is something that looks like a solution but is not actually a solution, hence the reason why I am encouraging you to check your work when you are done. When we raise both sides to an even power, like I did on my step here in order to clear out the radical sign, we need to be careful. It's going to generate sign errors potentially, and in this kind of sneaky way, because I was able to naturally flow down to an answer that claimed that x was equal to 25. So again, I know I've said it so many times already, but please check your work before you claim that you have found answers. Let's continue and take a look at the following two problems. So here we have the square root of x plus 5 minus 9 is equal to 11. So I'm going to go ahead first and clear out anything that is not connected to the square root. So I'm going to add 9 to both sides. And this is going to leave me with the square root of x plus 5 is equal to 20. So at this point, you can kind of do a little check right now, like I had shown you in the previous example. And I'm showing that the principle of the square root is equal to a positive number. That's expected, so I should definitely keep going here. So in order to clear out this radical, I'm going to square both sides of the equation. The left-hand side will now become x plus 5, and 20 times 20 is going to give you 400. Finally, we're going to remove 5 from both sides of the equation in an effort to get x by itself, and this is going to give me x is equal to 395. So we should check this. And in this instance, again, as you go through the steps, you will see that you do get a true statement. 20 minus 9 does equal 11. So for our next problem, what I want us to note is that this only looks different on the outside. So this might start to look a little bit more familiar if we were to write this using radical notation. So instead of x is equal to x plus 10 raised to the 1/2 power plus 10, we can write this as x is equal to the square root of x plus 10, and then keeping that other plus 10 outside of the radical. So from here, we're going to go ahead and use our same process as demonstrated before. So I'm going to go ahead and subtract a 10 from both sides of this equation. So in doing that, it's going to clear the plus 10 on the right away, getting my radical isolated or by itself. So from here, we have x minus 10 is equal to the square root of x plus 10. And we'll go ahead and, in order to get rid of the square root, we'll square both sides. So this is going to generate a little bit of an aside here, or I'm going to do an aside. In other words, I'm going to kind of think on the side of my page. And I'm just going to take this time to go ahead and actually FOIL out x minus 10. Remember that x minus 10 squared is going to be x minus 10 times x minus 10, so that means that we're going to have to FOIL. So in doing this, we'll get x squared minus 10x minus 10x, and then plus 100. From here, we can go ahead and combine like terms. This is going to give us x squared minus 20x plus 100. So let's go ahead and put this back into our original problem here. So I'm going to substitute my work here. So x squared minus 20x plus 100 is now going to be equal to just x plus 10. Remember that the square root and the square will undo each other. They're inverses of one another. So from here, it looks like I have a trinomial on the left-hand side, and it looks like I can still combine like terms. So what I'm going to do is I'm going to clear the x, and I'm going to clear the 10 from the right-hand side. So in doing that, I will subtract an x from both sides, and I will subtract 10 from both sides. This will give me a result of x squared minus 21x plus 90 is equal to 0. So from here, we'll want to see if we can factor this down. So it turns out that this is factorable, so you could use your quadratic formula if you would like, or you can try to factor this. If you factor it, you should get x minus 6 times the quantity of x minus 15 is equal to 0. If you don't believe me, please go ahead and pause the video and actually FOIL that out and see if you do get a result of x squared minus 21x plus 90. If you do believe me, let's go ahead and continue on. So we can use our zero product property here. So we're saying if this quantity, or this mystery number of x minus 6, times this other quantity, or this other mystery number of x minus 15 is equal to 0, then we should be able to kind of guess or state that either the mystery number of x minus 6 is 0, or the mystery number of x minus 15 is 0. From here, we can go ahead and solve for x. In one case, we're saying our answer is x is equal to 6, and then in our other one, we're saying that x will be equal to 15. But of course, we should double check our work. When we do take a look at the checks, so when we put our solutions back into the original equation, we get the following statements. When I put 6 in for x, we get the statement 6 is equal to 14, which we know this is a false statement. So as a result, we're going to remove x equals 6 as one of our solutions. This is going to be an extraneous solution. In the case of our other answer of x is equal to 15, when we put that back into the original problem, we do get a statement that says 15 is equal to 15. This is a true statement, so this confirms that this is one of our solutions. Okay, so now it's your turn. Go ahead and try your hand at these two problems. Make sure that when you are solving, be sure to check for extraneous solutions. And remember, you'll know that you'll have an extraneous solution when you are given a false statement from your check. When you are ready, go ahead and press play. So for our first problem, the square root of y plus 4 plus 6 equals 7. We'll clear 6 from both sides, and then once we have the radical isolated, we're going to go ahead and square both sides. This will result in y plus 4 is equal to 1. We'll remove 4 from both sides to get y isolated, and we get that y is equal to negative 3. Looking at this check, we can see that we do have a true statement, so y equaling negative 3 is a solution. Okay, so returning back to the fourth root of 5y plus 31 is equal to 2. So notice here that we're working with a different index. So in order to undo a fourth root, we're going to have to raise it to the fourth power. So they have to match each other. So once we do that, we get 5y plus 31 is equal to 2 raised to the fourth is 16. We'll remove 31 from both sides to get 5y is equal to negative 15. And when we divide, we once again get y is equal to negative 3. That was completely accidental when I picked these two problems. And when we check, it does look like everything works out. Yes, we do at first have a negative 15 plus 31, but when we combine those two values, we do have a positive number underneath that even indexed root. We can take the fourth root of 16, that is 2, and 2 equals 2, so this is a true statement as well. So in this particular case, these two problems, neither one had any extraneous solutions. And that's kind of an important point to make. Not every problem will have extraneous solutions to it. So again, that's why it really pays off to check and make sure that everything works out. All right, you are ready to move to the next video.